you've got a good background in geology starting now, right? So it's like you know about how atoms and molecules and things like that can go together to form minerals. And minerals, in fact, the most important variety of those are the silicate minerals. And so, and you've learned what kind of rocks you can make out of these minerals as well. So now we're going to get on to what's inside of the Earth. And well, you can see what's inside of the Earth, right? Here's a cross section of it right over here. Somebody cut a wedge out of the Earth and we can take a look at it. Oh no, you can't do that. In fact, how do we know what's down there? How deep can you dig? Well, probably not deep enough. People have tried it, right? And so, yeah, so you can't get into the Earth from the Earth's surface deep enough to figure out what's inside of it. So we have to use indirect evidence, in fact. So we use evidence from a lot of different areas, and so we're going to talk about that today. And then once we talk about the Earth's interior, we're going to talk about plate tectonics. How does the Earth work then? And so here we go. Buckle up. We have some questions remaining. How thick is the crust? Well, you kind of have an indication about how we figured that out. How thick is the mantle? Well, that's a little bit more difficult to figure out, but we'll get into that. And then how thick are the interior layers? All the layers in between. And what are their compositions? What are they made out of? What are the physical properties that are in the interior of the Earth? So is it solid? Is it liquid? Where's the partial melting? Is there a liquid in there? Is there solid in there? So what's the composition of the outer core and the inner core? We're going to answer those questions today. And so how do we know all of this? Well, if we did dig a hole, we could do that with a drill rig, right? And so they've tried that, in fact, in Russia, in Siberia. I think it was in the 1970s, actually early 1980s, that they began to drill. They call it the Kola well. In fact, if you went on Wikipedia, you could look up the Kola well. It was at one point the deepest well ever drilled on Earth. It was 12,262 meters deep. Okay, you multiply that times 3, and that's about how many feet it was deep. Okay, a little bit maybe more than that, so maybe 4. So anyway, it's roughly around 40,000 feet deep. Now, we drill wells sometimes in Oklahoma down to almost 18, 20,000 feet deep just to recover oil and gas. And this one in Russia, what they recovered was, well, as it turns out, it was a type of crustal rock that you know as gabbro, essentially. So there's gabbro. The trouble was, when they were drilling this, they actually kept drilling, but the borehole was so warm that the rock would come in and close off the bit. And so they got a stuck bit down there a couple of times, I think, actually. They were able to extract it and then try to go on, but they had to stop eventually. People who compete for these sorts of awards, I guess you could say. Well, they tried that in Qatar also. So Qatar is one of the Persian Gulf states. And in Qatar, they drilled a well just a little bit deeper than what they had drilled in Russia. And that was 12,289 meters deep in Qatar. And I don't know if they produced natural gas out of that or not, but that's just a little tiny bit deeper, another 27 meters deeper, right? So what's that, 54 feet, 60 feet maybe? Not to be outdone, the Russians drilled a well then in the island of Sakhalin. Now, Sakhalin is off the coast of eastern Russia. It's kind of situated in between Vladivostok, a little bit north of Vladivostok, and then in Japan. And so it's in that northern part. I think they call it the Sea of Japan there. But anyway, that is where they drilled the next well, and they drilled it, of course, a little bit deeper than what the Qatari well was. And so there are monuments to these things, actually. So if you get in Wikipedia and if you look up the deepest drilling rig, and the Kola well was the deepest one for a long period of time since the 1980s, and then Qatar, and then Sakhalin here. We've hand dug mines also in search of minerals, in search of gold, in fact. So the deepest mine on Earth goes down 3.5 kilometers. So if that one was 12 and a half or 12 and 13 and almost 12 and a half kilometers deep, we go 3.5 kilometers deep and we put people in it. And that's the gold miners who were in well, they're in South Africa, and so the temperature is so hot down there, in fact, that it gets up about 130, 35 degrees. And of course, that's not from the sunshine, that's from the geothermal heat that's down there. I think that's Witwatersrand area of South Africa. And so, but they find gold down there. And so that is pretty much the extent of where we've been able to go and know what's down there with confidence. Well, we trust these other methods too. So in fact, we have to use indirect evidence in order to see what is down there. One of those relies on the fact that we think that there was a planet somewhere between Mars and Jupiter that had broken up early in the formation of the solar system. We talked about the origin of the moon. It was roughly about that same time that a planet, maybe just a little bit shortly after that, that it broke apart from the tidal forces of Jupiter. Jupiter was so close in orbit to this other planet that this other planet just eventually broke to pieces. And today we know that area as the Asteroid Belt. And so the Asteroid Belt has clumps of asteroids on either side orbiting around the sun as Jupiter does. And so Jupiter kind of swept up a bunch of the debris from that planetary breakup. And then some of it actually went crossing across the rest of the inner planets out here. And so we get craters associated with that breakup as well. So we worry about things actually like that because we know it was an asteroid or at least a comet that came in and wiped out the dinosaurs as we know it. And that's the same risk that we face today, in fact. And so it's not a matter of if it will happen again, it's when. When is it going to happen? So NASA's been tasked with this sort of opportunity to try to figure out where these near Earth objects are. If they're larger than 1 kilometer, now they've scaled that down to what if it's 400 meters across? That could cause a lot of damage as well. And that is correct. And so they can cause extinction. We're worried about that for our survivability on this planet. There's 2 things you can do. You can burrow in and try to hope that the impact doesn't kill you, or you can go to another planet where only one of the planets will be wiped out by a meteorite impact. So, the dinosaurs didn't have a good space program. They were able to fly, however, and some of the dinosaurs made it through that extinction event. The avian dinosaurs, right? And so how do we know about the interior of the Earth? It's from those meteorites. In fact, we don't have any that was related to the meteorite impact necessarily from the asteroid belt that wiped out the dinosaurs, but in fact, we have meteorites that collect on Earth every year. There's about 3 million tons of material that the Earth sweeps up from outer space. Now, these meteorites can come from a lot of different places. So when there is an impact on Earth, it could blast things out, and even Mars could then sweep up the remains of that. And so we actually have pieces of Mars that have made it to Earth. So if there was an asteroid that hit Mars, it could eject material out of that impact and throw it all the way into Earth's orbit. And we've swept up particles like that. We swept up chunks of rock from places like Mars and the moon and a few other places. But in general, meteorites are then a way that we can look at what we think was in the interior of another planet. And I've already talked about that a little bit, but we'll talk about it a little bit more here. We also know about the interior of the Earth from some other indirect methods, and one of those is listening very carefully to what's going on down there. And so if you put sound inside of the Earth, it's going to be reflected off of layers in the Earth. There's an acoustic impedance at different layers, and we get the reflection off of that. And we either get the reflection or the refraction off of that. And so we can determine then what the behavior was like. How quickly did those sound waves penetrate through the Earth, and can we, record what was down there? There's some complications with that, but it's a very interesting sort of technique, and we've gotten really good with using computers to help us calculate what those velocities are, and also what the temperatures are. And so that's another indirect way that we do it. We also know that there are pieces of mantle sometimes that fall into magmas that eventually make their way up to the Earth's surface. And those things are called Mantle Xenoliths. And so that's how we kind of know about the composition a little bit of these, of the mantle, at least of the upper mantle part anyway. We're not quite as certain about the lower mantle, but we're kind of working on that. And so that's another story for a little bit later in this presentation. And then lastly, we know that temperature increases as you go inside of the Earth. We also know that pressure increases as you get inside of the Earth. So we have an instrument that helps us measure the changes in those minerals. They shoot lasers at it eventually, but there are two diamonds that come together and compress a material, and we can study Earth materials that way. So what happens to a mineral once you get it under a lot of pressure and you turn up the heat? So those are experimental ways that we can get at what's in the interior of the Earth. Okay, so let's start with the meteorites first. This is a great one right here. In fact, this is a Stony iron meteorite. It's not completely stony and it's not completely iron. It's mostly stony. And so, but that is one variety right here that you would find if you could slice the Earth open. That's what we think that the Earth's mantle is made out of for the most part. Now, these are Stony meteorites or Stony iron meteorites. And so this one, in fact, has a low content of iron in it, so it's more of a Stony meteorite here. I need to change that in my presentation here, so I'll change that so you get a corrected copy here. I have Stony iron down here. This is really a Stony meteorite right here. So it's got a chip broken off the edge right there so they can see what was inside of it. But if you look at this thing, okay, so I get people all the time come to me and say, is this a meteorite? It's like, no, it's not a meteorite. I have yet to see a single meteorite brought in by anybody in this, 30 years that I've been doing this sort of thing. If you look carefully at this rock here, you can actually see melted material on the outside. That's called a fusion crust. And that's what you'll typically see with meteorites because they have to fly through the atmosphere before they hit. So that's a Stony meteorite right here. The next one here is kind of a Stony iron meteorite. So this one's the Stony iron meteorite here. It's a palisite. That's the name that they give this one. And if you look carefully at this, there's rock in it. There are minerals in it, in fact. And so there's also minerals that are made out of metal. Okay, so that's the iron nickel part of this meteorite. So the name palisite comes from this sort of mosaic of, as it turns out, these are olivine crystals. So olivine was the major component of the Stony meteorites. It's also a major component in the Stony iron meteorites. Well, if we think that nickel and iron are at the Earth's core, this would be close to that boundary between the core and the mantle. And so this would be like core mantle boundary material right here. And so what you see here, it's projecting light from behind, and you see the green crystals and the yellow crystals in here that are forsterite and phaelite, actually, or two varieties of olivine here. And then the metal crystals that are around it, in fact, are taenite and kamacite mostly. And so there are minerals, too, that form out of metals as well. And so they crystallize that way. So that is a Stony iron meteorite. You've seen the Stony meteorites. And now we're going to look at the iron nickel meteorites, or nickel iron meteorites. And so this is the world's largest meteorite, at least the one that's still preserved at the Earth here. It happened to have hit in the middle of a desert, and of course they found it, and then they began to excavate around it. And so this is called the Hoba meteorite, and for the longest time they didn't have it fenced off or guarded or anything. People would take chunks of it, but in fact that's the world's largest meteorite, and it's a nickel iron meteorite. And it's protected now. It's not the only one. There's a lot of these that hit the Earth, but most of the ones that hit the Earth are Stony meteorites. And from the proportion of different kinds of meteorites that strike the Earth, well, first of all, you could already suspect that the core mantle boundary must be much smaller than what the core or the mantle are. And so those are the rarest ones. And so palisites are extremely rare meteorites and worth a lot of money. But these iron nickel meteorites, much more common, in fact, but usually you don't find them this big. Okay, so they usually are a little bit smaller than that. That's the sort of meteorite, in fact, that struck at Meteor Crater. When you go out to Arizona and you see a sign that says Meteor Crater over this way, 7 miles or whatever, off of the interstate highway there. And so it was an iron nickel meteorite like this. It's called the Canyon Diablo meteorite, and probably from the same origin, in fact, from the Hoba meteorite here. Both of them coming from the asteroid belt and then landing on Earth at some point. And so the Canyon Diablo meteorite's pretty cool. I used to have a little chunk of a Canyon Diablo. We still sweep up pieces of meteorite from that asteroid belt. I also have a little tiny chunk of one called a Sokote Alin, and that fell in eastern Russia in 1947. So really amazing, these sort of things. And so, yeah, pallasites are pretty common. There's one that hit in western Kansas. It's called the Brennam Meteorite, and so, but it's a pallasite. And the largest pallasite is roughly 2 or 3 feet by 2 or 3 feet. So it's amazing how these things, have come to visit the Earth. And so here we have this meteorite that's the world's largest right here. What do they look like on the inside? What we think is the center of the Earth is solid. And so if it's solid, it had to have crystallized. And so what they find is when you cut these iron nickel meteorites open and then you slightly etch them with acid, like fumes of nitric acid or some other acid like that. First of all, you polish it and then you get it down there and then you etch it with a little acid and the crystal form shows up then. And that's called Widmanstätten structure here. It's a German word, obviously, but it shows the crystal form, and these were intergrowing crystals that make these lines and angles like this. And of course, it depends on how you cut it. And so the orientation of the mineral relative to how it's been sliced open is pretty important. And so this is one that's been sliced in a certain direction. And so normally these things will form like complex three-dimensional sort of structures. But you'll see these sort of lines that go through it once it's been etched this way. And that's that Widmanstätten structure. We have never been able to duplicate, humans have never been able to duplicate this sort of crystallization in an iron nickel meteorite. Now you think iron and nickel are the two principal things that are in stainless steel, right? So you would think that we'd be able to get it to crystallize. No, you can only get little tiny crystals on Earth for the most part. Widmanstätten structure takes millions of years for these things to form. I supposed if we could duplicate the circumstances, the pressures and the temperatures that may have been in that other planet, we might be able to then duplicate that, but that has yet to be shown that you can do that. Maybe at some point in the future, maybe in your lifetime, they'll be able to duplicate Widmanstätten structure. But what it does, it tells you that there's extremely slow cooling in planetary cooling processes. And so we think that came from the core of another planet, essentially. So the asteroids were derived from another planet. They visit Earth every once in a while and cause havoc sometimes too. So if that is one of the principal ways that we have indirect evidence for what's inside of the Earth, another way is through the seismic events that we have on this planet as well. Now, we haven't talked about earthquakes yet, but we will talk about earthquakes quite extensively in here. And this is a map that shows you where all of the epicenters have been for earthquakes since 1898. And it says it's by magnitude, but most of the large ones in the last, since 1898, there have been maybe 5 or 6 that are in the category. We call it a magnitude. And it was a magnitude 9 roughly, or 9.5 is just about the largest earthquake that we've experienced in the last 130 years. So, in fact, what you see on here, the 3 biggest ones recently anyway are the Banda Aceh earthquake. I think that was pretty big. The one in Fukushima was fairly large as well. But two of the bigger ones, actually, there was one in Chile on the west coast of South America that was a 9.3 or 9.2 back in 1960. And so in 1964, there was another major earthquake that hit in Alaska, and they call that I think it was the Turnagain Arm earthquake, but it was the Good Friday earthquake. So it happened on Good Friday of 1964. And so both of those latter two earthquakes generated a tsunami, and even Fukushima generated a tsunami that was felt on the west coast of the United States. So in the Alaska earthquake, it actually was able to kill people in Northern California with the tsunami. And the Chilean earthquake in 1960 caused a tsunami in Hawaii, and it killed people there. So tsunamis and earthquakes are very dangerous. So what we know about earthquakes is they always occur at faults, and they always occur where there's some sort of breakage. And when it breaks like that, those waves get emanated through the earth, but they don't usually occur deep inside of the earth, as it turns out. So the deepest earthquakes that we know of are only about 600 kilometers deep, so 400 miles deep inside of the earth. If you get much below that, everything behaves in a different way. And so, but it's only this outer part, that 600 kilometers and closer to the surface, that we get rocks that are solid enough to break and behave elastically, we say, and send out seismic waves through the earth and then around the earth. And so that's one of the other ways, and indirect evidence. So we have earthquakes. We're going to talk about this a little bit more when we get into earthquakes, but know that you're going to see this diagram again. So if we have one of these earthquakes, it's pretty close to the surface here. They're showing you an epicenter over here. Now that looks like it's over in Greenland somewhere, so that's not bloody likely, because there's not very many active plates up in that area, because you can see the United States over here on the left side, and you can see South America over here on the lower left side. But they're showing that seismic event pop. It's a lot like sound waves that travel through the earth, and so it puts things in motion, essentially. And so if you can imagine a very, very low frequency sound that travels through the earth, and what it does, it kind of emanates outward, and because the earth is denser at depth, those waves can go through that dense material even though it may not break down there. And so even through plastic materials like inside of the earth, you can get the waves that will plow through, be heard through there. Okay, let me use an example. In the Old West, when Native Americans were roaming the high plains of the United States, they could put their ear down and tell when a train was coming, because of the vibrations that were given off by the train miles and miles away. And so they understood, that transfer of energy in the form of sound waves. And it's the same thing that's going on here. If you put your ear to the ground a ways away from that seismic event, you're going to be able to hear it. We don't hear it with the human ear. We have to use a instrument called a geophone, essentially, or a seismometer or a seismic station. So seismic stations can record those vibrations that we can't necessarily feel ourselves unless we're right near the epicenter of that earthquake. So we have these sort of listening devices all around the world, and they detect two different kinds of waves. Some of those waves travel in one pattern, and some of them travel in another pattern. When we talk about earthquakes, you're going to learn this, but it's called P waves and S waves. P stands for primary, S stands for secondary. But the behavior is that the P wave goes like a sound wave and travels straight ahead. The S wave has a tendency to go side to side, and it's a shear wave as well. And so when it shears, it goes, and it takes a little bit longer time. So the primary wave shows up first. The secondary wave is the shear wave, which shows up second. And then we've found from listening around the earth to what these waves and how they go through the earth, where we don't hear them. And that's really important. And so there are two areas on Earth that we recognize. One of them is called the S-wave shadow zone. In other words, there's an area on the opposite side of the Earth where you're not going to hear that seismic event in the S-wave. And you're not going to hear either an S-wave or a P-wave necessarily, but there may be parts of it where you hear a P-wave, but you don't hear the S-wave. And so that's what this illustrates here. So you can see where the P wave and the S wave shadow zone overlap, you don't hear anything. But in the very opposite of the Earth, they call it antipodal, on the opposite side from that seismic event, you can hear P waves because the P waves travel right on through, but the shear waves cannot make it through the interior of the Earth. So the shear waves, as soon as they hit the core mantle boundary, they actually convert to P waves. A lot of people will say they stop, but they really don't stop. That energy continues on, but it actually goes through a phase transition and it goes into a P wave. And so that P wave travels on through the Earth and gets recorded on the opposite side of the Earth. And if you hear about earthquakes, like there was one recently, it was an 8.1 in the Tonga Arch. I think that was on Wednesday of this week. I mean, this is Friday right now while I'm recording this. So on Tuesday or Wednesday anyway, there was an earthquake on the Tonga Arch, a very active seismic area. And that earthquake was felt around the world, and you can actually see the recordings in some of these. So they have a seismogram, which will record the actual event itself. And it takes some time for it to get there, of course, right? So with the distance is equal to some component of time, and with the S waves and the P waves, we can really kind of understand what the interior of the Earth is all about. And so the seismic event travels through in a wave front and then may get reflected as well. And so you can actually see multiples of that seismic event, perhaps. We can do that artificially, too. We don't have to rely on earthquakes. Nuclear bombs, that's how they detect nuclear bomb detonations, is with seismicity. But then also we can use artificial means to put waves into the Earth. You've probably are familiar with people driving down the road with a big subwoofer in their car, and you can hear this, that sound is just like vibrating everything around it, and you feel it as they go by. In fact, it becomes a distorted frequency that it's called a Doppler effect. When it goes by, it kind of slows down the waves. And so everything seems a little bit slower when you go by, but it compresses it as they're arriving, right? We do the same thing by putting a subwoofer on top of the Earth and cranking up the volume to 11. And they have trucks actually that do that sort of work. They lower this acoustic instrument against the Earth on a trailer. It's hauled behind on a trailer, and then they stretch out geophones to be able to detect the vibrations as they return back. Well, those things are called reflections. And so the reflections come back to the top surface of the Earth, and we record those. And so that's what you see in this diagram, in fact. So with this diagram, you can actually see where the reflections kind of stop down there, and that's near the base of the crust. So we call that the moho. So where the waves travel with a certain velocity, and then they kind of slow down a little bit after that. And so that's an area right there. I think it slows down. We'll check that out. But anyway, it hits the moho here, but they get reflected back. And so on the left-hand side is the data. On the right-hand side is the interpretation of that data. So the moho is called the Mahorovich seismic discontinuity. That's why they call it the moho. It's just easier to say. But it marks the base of the crust. Now, as we talked about previously, these tectonic plates are made out of crust plus the upper mantle. And so the subcrustal upper mantle and the crust together go together to make these tectonic plates. So just because you're at the bottom of the crust there doesn't mean that's the only thing that moves across the surface. So that moho is somewhere between 0 and all the way down to 70 kilometers deep inside of the Earth. So these discontinuities like this, you get different densities of material down there. And so when you go from the crustal material into the mantle, you're going into an olivine-like material when you're in the mantle. So that subcrustal upper mantle, more like olivine. And so you get seismic discontinuity there. Actually, I think it speeds up a little bit right there. And then a little bit lower, like about 250 kilometers, 200 kilometers, it slows down again. And that's where we get a zone of partial melting. Well, that's the base of the lithosphere. And so there's crust, there's subcrustal upper mantle, and then there's lower mantle down below. Below the asthenosphere, actually, it's lower mantle. But the asthenosphere itself goes down to about that 600 kilometer limit where it's no longer brittle once you get past the asthenosphere. So if you're keeping track now, 0 to 70 for the crustal material at the top, and thinner on the oceans than it is in the continents. Continents get up to 70. So 0 to 70 is crust. 70 or so actually goes to 0 at some places, but it goes down to 250 kilometers where we get to the base of the plates, right? So it's spreading centers in places like that. There's new crustal material being added there. So you're actually at the top of the mantle, essentially, there in the subcrustal upper mantle. And then there's a zone of partial melting at that 250 kilometer level, roughly. And below that is what we call the asthenosphere, and the asthenosphere is still rocky and capable of breaking, but it's a below that zone of partial melting at 250. So at 600 kilometers, there's a major discontinuity as well with the seismic velocity, and then we can go all the way almost to the core mantle boundary before we hit another layer boundary then. So it goes asthenosphere, lower mantle, and then there's a layer called the D double prime layer. And then we get into the core after that. And so in the core, in fact, we have a liquid outer core and a solid inner core. So that geologic layering like this helps determine how we understand the Earth. I mean, how we understand these thicknesses is based on the seismicity. Okay, that's the number one way that we understand the thicknesses of crustal material. So here we have it here. This shows the crustal thickness, and you can see in the Himalayan mountains where there have been two continents crushed together. The subcontinent of India has crushed together with Asia, and so that formed the highest mountains on Earth in the Himalayas, and that's 70 kilometers thick here. It only gets to 60 kilometers thick in the Andes Mountains out here, but across North America, the continental crust is roughly 45, kilometers deep. In Missouri, I think it's somewhere between 42 and 44 kilometers deep before you finally get to that subcrustal upper mantle. Excuse me, you get to the subcrustal upper mantle at that depth. And then that goes on for another 200 kilometers or so. So here are the various seismic profiles that you will see if you had a source at the surface and it projected into the Earth, and you could measure the velocity at which it returns. These are the projected velocities in the Earth that we've been able to model. And so what you see here is a white line that shows you the density, and then you can see the shear velocity, which is slower than, that's going to be the S waves. And then you can see the compressional wave velocity, that's the P wave velocity. So 3 different lines on here. And so what you see is it speeds up when it gets to the bottom of the crust there. That's that long directional to the right there, the deviation of that line to the right. So it goes from 6 to 8 kilometers per second, the seismic velocity when you get to the base of the crust. And that's the moho. So that's the moho right there that you can see, that the flat line that runs off to the right. And so you see that that's what we base our density estimations off as well. So that's going to be when it hits the olivine layers, right, in the subcrustal upper mantle. So that's the top of the subcrustal upper mantle there. And then it goes down to about 250. So on the left-hand side, you can see the depth over here. On the right-hand side, it shows you the pressure because we know the pressure increases, right? So with the depth over here on the left-hand side, if you follow that down to 600 kilometers, which is just below that tick mark there, you can see that there's a shift back to the right where it increases velocity after that. But if you follow the line up from below the moho, there's a little divot in the line there that heads to the left. That's called the low velocity zone. And that low velocity is explained by having a partial melting zone there. And that's about 250 kilometers deep, or 200 kilometers. It's marked in this diagram here. But roughly at 200 kilometers deep, there's a low velocity zone where there's partial melting. Well, that's the surface on which the tectonic plates will move. And so it's like having a little bit of water on ice that makes it very slippery right there. So the subcrustal upper mantle and the crust behave together, stick together essentially. And then below that, there's a zone where you get some shearing, essentially. And so it has a low velocity zone there. And then up at 600 kilometers again, it increases again. That's the base of the asthenosphere. So the asthenosphere goes from 200 to 600 kilometers deep. And then the mantle goes all the way down to this D double prime layer, which is right near the core mantle boundary. And so that goes down to 2,700 kilometers roughly here. on this diagram. And so that's the lower mantle, and then almost to 2,900 kilometers, that's the D double prime layer here. And so below that, we have the seismic waves go through that transformation, and we lose, if you look on here, we lose the shear waves, right? So the shear waves disappear right there. But then they show up again when you get to the solid inner core. Well, they go through a phase transition where they become a compressional wave in that liquid outer core. And then they become a shear wave again once they hit that solid inner core, and then it, boom, pops it back out to a shear wave again when it reaches the other side of the Earth and hits that core mantle boundary again. Oh, no, actually, it never comes back again right after that. The shear waves never make it back. But anyway, that's kind of a cross section of the Earth here. So in other words, the green material up at the top up there, that's the asthenosphere and everything that's above the asthenosphere. So that would include the subcrustal upper mantle, the zone of partial melting, and then the continents at the very top up there, which are marked by that seismic discontinuity, the MOHO. And so with this material at the bottom here, you have the liquid outer core. Compressional waves go through it, the P waves go through it, and then you have the solid inner core there at the bottom here. That is the most important part, I guess you could say, about knowing what we know about the interior of the Earth from this seismic velocity. Meteorites, seismic, but we've got two more to get through, okay? So we're not quite finished yet, but that is the structure as we understand it. If we just want to know what's below the crust, we look to volcanoes. In volcanoes, that's where we get these pieces of mantle that get incorporated at that zone of partial melting and get drawn up into the crust as these things erupt at the surface. And so there's only a few places around the world where this happens. Some of those would include, like, there's some in Nevada, okay, where the mantle has been thinned a little bit in Nevada. And so some of those Mantle Xenoliths makes their way into the volcanics that have erupted in central Nevada. But also along a sort of boundary in Arizona that runs across Arizona. And so we have an area in North America, we call it the Colorado Plateau. Right at the edge of the Colorado Plateau, there seems to be a mantle upwelling a little bit underneath of the Colorado Plateau. And you get pieces in the volcanoes around the southern perimeter of that tectonic area right there, the Colorado Plateau. You get these sort of pieces here. That's olivine. I mean, it's dunite, really. It's olivine plus some accessory minerals in there, but they get incorporated into those volcanic rocks and then brought up to the surface. You get the same sort of rocks like this that you see here. These are, I think that's one of my samples, actually. You see the same thing in a few other places around the world. Where you get mantle material incorporated into the volcanics. This is one from the central part of the Indian Ocean, and so this is from the Kerguelen Islands in the center of the Indian Ocean, and so that's what you get in these volcanoes, pieces of mantle that may come up. Now, xenolith, what's the name of that? Xeno means foreign, and lith means rock. So in other words, it's pieces of mantle rock that are going to get incorporated into a magma, and eventually that magma is going to find its way to the Earth's surface. Mantle Xenoliths. That's the third example for what we have for understanding the interior of the Earth. Now, that's just barely below the crust. Okay, we're talking in that zone of partial melting, things are falling into it from the mantle, or at least being stoped into it from the mantle, being fed into that magma chamber from the rocks that are around it. Now, this is the final variety here. Now, this is from Carleton College over here on the left. And this young woman here is working on what they call a diamond anvil cell. In the old days, they used to call it a diamond anvil press. But a cell, what they do is they take a little tiny piece of sample and they load it into that instrument. And there are diamonds. Remember, the diamonds are they're the hardest substance known to mankind, right? And they take two diamonds that have been beveled flat at the top surface there, and they put it into a compressional device, like a vise, if you will, and they turn up the pressure. So hydraulically, they increase the pressure between two diamonds, which are extremely hard, in other words, resistant to abrasion. And then they have a small area where that sample essentially is experiencing massive amounts of pressure between two diamonds. And so that's the diamond anvil cell right here. And when they do that sort of process, you can actually get one mineral to change to another mineral under enormously high pressures. How much is the pressure? I think it's like 10 gigapascals. It's an amazing amount of pressure that you can get in a very small area. So when they do these sort of things, I think it can be a little dangerous. I know that rock mechanic labs can be very dangerous, where they try to compress rock core, and the rock core, if it fails, you can hear it, all over a campus if they're testing it. So you have to be very careful with these sort of instruments under enormous amounts of pressure. They use that laser, I think, to try to determine how the minerals being reoriented, and so they can actually find out how the crystal lattice is reflecting changes that mineral is under, the sample mineral is undergoing under that pressure. And so that's what the laser is for here. So we have mantle. We have the crust that's 0 to 70 kilometers thick. There's ocean crust, there's continental crust. Ocean crust is 3.0, its density, right? 3.0 grams per cc. The continental crust is 2.7 grams per c, essentially the same weight as quartz, if you will. So if those are the two parts of the crustal material, what's the mantle made out of? Well, it's made out of essentially olivine for the most part, but olivine that will reorient it, and it can be reoriented and form new minerals, but it's still going to pretty much look the same. And so it's almost all rock except for that zone of partial melting that's roughly about 250 kilometers deep. The temperature goes up, the pressure goes up, the density goes up with depth. All three of those parameters go up. The seismic velocity increases until you get to that low velocity zone at 250, but then it increases again at 600 kilometers, and it stays relatively fast all the way through the mantle until you get to the double D layer, or D double prime layer. And so when it gets down there, it changes a little bit, but not a lot, but enough to notice that there's a layer there. And then things kind of slow down when they hit the material that's in the core. So the mantle is ductile. Okay, so below 600 kilometers, if we get earthquakes down to 600 kilometers, that means it's brittle still. You can still break that rock under enough pressure, and you can cause it to generate shock waves or generate seismic waves. With the lower mantle, then at 600 kilometers and lower, we're talking about a material that is unlike anything you may be familiar with. It's a solid still, but it's a solid that can flow. In other words, you can take a solid and make it flow. Well, this may make some sense if you think about glaciers, right? So glaciers are made out of ice. Ice is a solid, right? But glaciers will flow because under pressure, they begin to flow outwards, right? And so that's the same sort of behavior that we get in the lower part of the mantle, in fact. So it is a material that we would refer to as being plastic or ductile. Ductile and plastic, same connotation there. You can bend it, but it stays the shape that it was bent. When we're in elastic materials, which is that upper 600 kilometers and all the way to the surface, that's either brittle, where you break it, or it's elastic, where it snaps back to its original shape, like an elastic band. And so those are three of the types of behavior that we have in the earth. Brittle behavior, where you can take a pencil and break it, or you can take a pencil and you can wiggle it a little bit and cause it to bend a little bit. That's elastic behavior. Or then you can get something like silly putty, and silly putty will actually begin to flow. Well, it's not its original shape. You can make a little line out of it, and then it will begin to deform then. And so that's what you get in the lower part of the mantle. Now, if the mantle is 2,900 kilometers deep, and that's pretty deep, okay, so, when you get to the bottom of what is that, 3,700 kilometers deep? Anyway, it's pretty deep. And so that's the center of the earth, essentially. When you do a calculation, and I always ask students, do you know how to calculate the volume of a sphere? We know how deep the base of the mantle is, and so we could actually calculate the volume of the entire Earth and then subtract off what the volume of the core is and what you're left behind with. So the mantle makes up the majority of Earth, 75% by volume. And it's that 25% that forms the core. And so 25% of the Earth is the core, 75% of the mantle. Here's the weird thing then, okay? So when you do calculations based on how many meteorites actually strike the Earth, the Stony iron meteorites are roughly 3/4 of the meteorites. And so this other planet probably had the same proportions that Earth had. So it has right now. So hopefully we won't blow up like that other planet. These minerals, okay, so that explains the volume. Oh, by the way, the formula for calculating the volume of a sphere, it's 4/3 pi r cubed. 4/3 pi r cubed. So that tells us that if we know the entire volume of the Earth, area, volumetrically, doesn't tell us about the density because the density changes, but volumetrically we have a certain density, and if you subtract from that the volume for the inner core, let's say, 2,900 feet, you could calculate 4/3 pi r cubed with that. So, ultramafic minerals include these silicate minerals, olivine, of course, and then you get a reorientation. You can form what we call spinel. Spinel has a sort of a dipyramidal shape like this, octahedral shape. So a four-sided pyramid stuck against another four-sided pyramid, that's spinel. And so that's the structure that's very resistant to sort of pressures. Provoskite is another mineral. And when you get deep enough into the mantle, you get what they call eclogite. But again, every single one of those is going to be mostly green or black. So that is the colors that you get with these minerals. So if the mantle is mostly ductile, except for the zone of partial melting there, and maybe a little bit of elastic, from 600 kilometers up, the mantle convection cells in that lower part can actually cause the exchange of heat from the core into the mantle and bringing it all the way up to where that zone of partial melting is, or maybe even higher sometimes, generating magmas in that partial melting zone. And so we have material that may make its way all the way up. We talked a little bit about this when we talked about volcanoes, when we talked about things from the D double prime layer, maybe sourcing these mantle plumes that will come up. Well, we also have what we think are convection cells inside of the mantle as well, like boiling water. So if you heat it up at that very hot outer core, which is still molten, it's a molten metal, so it's extremely hot, and it's heating up this rock, but it's rock that flows, and so it will actually essentially be boiling inside of the Earth and causing perhaps then the plates to move around it because they interact at the outer surface then. Kind of like the skin on a gravy, if you will. And so that material, that sauce that's at the top, it's more brittle, right? And so it comes around and interacts with other sorts of plates. And so that's how we think the Earth works, roughly. And so these convection cells are thought to lead to plate tectonics. There are some varieties of thought on that, however. And so some of the variety is maybe the act of subduction with one plate driving in and underneath another plate can also help to drive plate tectonics as well. Obviously, it has some sort of effect, right? So the D double prime layer, we think that may be the graveyard for these dead plates that get subducted. And so the D double prime layer, of course, is also the place where we think that these mantle plumes may arise from. So if we talk about the core, that's the one we know the least about, but they've discovered things just in the last couple of years here about the core. And so there's this outer core that we already know is molten because the S waves stop there. S waves, it'll slow down the P waves as well. And so we think that there was a differentiation when the Earth first formed. And so the heavy minerals sank to the center of the Earth. This is after the moon was formed. Okay, so if the moon was formed by that impact, it blew material out, and the moon got some of our core as well. And then it has its own sort of like mantle material and a thin crustal material, a thick crustal material on the outside of that. But on Earth, that internal heat could have been resided there for a long period of time. But then we have radioactive metals as well. those radioactive elements went to the center too, because most of those are pretty heavy too. And so they degenerate and they disintegrate essentially over time, and it generates heat. And so that's why we have this liquid outer core. And it was actually the inner core that we think is solid because of the work of Inge Lehmann. In 1936, she was a Danish scientist, and she's a seismologist, and she says, I think I see something inside of the core. And she discovered the inner core at that time in 1936. It was in 2015 that we discovered that the inner core itself has two parts to it. There's an inner core and an outer inner core that are both solid. But there's a different polarity somehow between them, and they spin at different rates even. So there's a detachment somewhere there inside of the Earth as well. Wild stuff that we can learn through seismic sort of processes. And also, if you can send sound waves into the Earth, there are other techniques that we use other than just the reflection seismology. And it's the same sort of principle that people use when they use acoustic wave sounds for like looking at young fetuses, right? So babies, right? So you can detect through ultrasound what is inside of something, and we can do that with the Earth as well. And so they call that it's a type of imaging. We'll get into that actually. It's a seismic tomography, they call it. So seismic still, it's sound waves, but the tomography shows us kind of the shape of the rock bodies in the deep part of the mantle. So we can't get that into the core because, the sound waves stop when they get, the S waves stop anyway, when we get to that outer core. Okay, so if that is the inner outer core, here's a slide. This is actually out of Science, the magazine Science, where they produce some of the cutting edge, you present some of the cutting edge. It shows you the polarity of the different aspects of that inner core. So it shows you the inner core and then the outer inner core. And then there's the yellow part around the outside. That's going to be the outer core, which is liquid, right? So there's different polarities to the rocks that are down there. Of course, they're highly magnetic. That's where we get our magnetic field from. And so that is the inner core right here in two different parts. Now, our next stop along the way, we've already talked about mantle convection cells. We've talked about the structure of the Earth from these four different kinds of understanding from indirect evidence. People still argue about what's going on in the mantle. It's not a resolved issue, but most people, most textbooks will tell you that it's the heating at the outer core that drives these mantle convection cells that will cause plate tectonics to form and actually cause the interaction of plates on the outer part of the Earth's surface. That's what they call the Plume Model. And so that's on the left-hand side of this diagram. So the Plume Model is this idea of mantle convection cells. And also we get the mantle plumes that arise from that D double prime layer. And so you can see that in the East Africa, the Afar Triangle here. So that's that sort of mushroom sort of shape that's on the left-hand side here. So what they're showing you here is that once you get subduction, also you can see the blue blobs that are going into the mantle there, being dragged down into the mantle by those convection cells, where the mantle convection cells collapse back in and get to be heated up again like boiling water, right? On the right-hand side, all bets are off. On the right-hand side, they call that the plate model. And that's one in which the proponents of that model suggest is like, well, there's not really these convection cells after all. But really what we're looking at is cold, dense, subducted slabs at various depths inside of the mantle. And so there are people who don't buy the Plume model, but instead propose this plate model. And the plate model actually is related to subduction. So maybe it's the subduction of these ocean slabs that are causing the spreading centers to form. Maybe they're being pulled instead of being pushed out of that spreading center. So that's a good question, actually. Which one is the correct way? And I have to tell you, your textbook is going to promote the Plume model because that's what most people buy into. And most people don't promote the plate model, but a few people do. And so, yeah, there's a volume published on this, and you see the 2004. I think I have a volume that was roughly published in 2008 that goes into all the arguments. And so they argue about this all the time. Well, that's what science is. It's argument based on evidence, right? So what's your evidence for this? What's your evidence for that? So every year they're applying new ideas to this sort of, well, it's a problem. How do we understand what's going on inside of the mantle? And so the volume was about that thick. It was like 4 or 5 inches thick. Made a good doorstop. It is amazing how much stuff gets written about some things that we can't understand even hardly, right? I'm a geologist, right? I read this and it's like, okay, I can kind of see I look at the pretty pictures and try to figure out what they're trying to tell me here. So that's what you do here as well. So this is an example where they've tried to apply both the models. That's the Plume model at the top there. That's the plate model at the bottom down here. And then in between that, that's the Mantle Tomography that they did underneath of Africa. And so they show you that sort of orange area that's kind of up and flickering like a flame underneath, right? Well, some people think that is a hot spot underneath of Africa there. And that's what caused the continents to drift away from Africa, 200 million years ago. In fact, that's heated material probably because it's less dense in that area. But that's always the question. So what's really going on there? Are those recycled pieces of slabs that have already been subducted that have detached and making their way up? That's what the bottom was tell you here. That's the bottom diagram down here is the plate model. The top diagram is the plume model. And I'm here to tell you, I don't know, and I don't know what to tell you other than your textbook says the plume model is what works. So in other words, that's kind of where it stands at this point until we find a better way to try to envision or try to see through remote means what's inside of the mantle. It's still a problem. And so, that's the nice thing. There's always going to be something that you can study when you're in geology. A lot of people think we know everything, that science is nothing but fact. But no, it's like we try to gather evidence to try to support or try to disprove something, right? And so that's the process of science going on. It's just that we haven't been able to resolve this one small part of it yet. Although there are clues that seem to support this idea of a plume model. So that's the upper one here. And so that's why they put it into textbooks, right? So what is the consensus? Well, that's the upper model here. That's the A slice on here. B was the evidence, and C is the other alternative hypothesis. So, and that's doing good science, actually. You have to question, if everybody thought one thing, we could go that way for a long period of time and never resolve what something is. And so, in fact, it's good to have arguments in science because it leads to a resolution, hopefully, at some point. And so here we have the two different competing models. Now, about plumes, this is sort of a diagram that shows you what most people think is happening in a plume. So if the D double prime is at the very bottom now, you heat that material up, it rises up, and then it kind of flattens out once it gets up to that, the upper part of the mantle up there, subcrustal upper mantle below the tectonic plates. And it kind of spreads out a little bit like a mushroom, right? So, in fact, I like to use the analogy of a lava lamp, they call these. Back in the 1960s, I remember my uncle had one of these, like 67, 68. He bought one of these. There's a light bulb at the bottom that heats up this gel-like material that floats upward. And in fact, I had one of these, except don't ever turn them upside down because they'll stop working on it. But if the material heats up, and then it goes up to the top, I think you have to reseal them if you turn them on their side slightly. But that is sort of what I like to envision as being part of these sort of mantle plumes. Heats up at the core mantle boundary at the bottom, rises up through the mantle, makes it up to the top, cools, and then it may fall back down, or in the case of some places, like maybe in and these large outpourings of lava that we've had in the history of this planet, it begins to form volcanoes at the Earth's surface. So that is what you get here. The mantle plumes they could be down to 2,000, 2,500 feet deep. How far across? They're about 100, 200 kilometers across. And remember, like in the Hawaiian Islands, we can actually track where the plume has been, or at least where the plate has been over the plume. And so the plate has moved over the plume, and it's left behind this sort of series of volcanic edifices that go all the way up to the Aleutian Islands. How long does it take for these things? Well, the Emperor seamounts, the oldest ones, 86 million years, but some people think that these things may endure for up to 300 million years. Now, the Afar Triangle has to be quite old, but recently, the Arabian Plate has split off of Africa, and so it's heading off to the north and east, and so in fact, Africa is beginning to split apart from the Afar Triangle as well. So that's one of the few plumes that everybody agrees upon. The other one, of course, is Iceland. And so Iceland and the Afar Triangle, for sure, are probably related to mantle plumes, certainly hotspots that are below the Earth's crust there. So if we were to look at the places where these hotspots occur, you can see the Afar Triangle, where the Arabian Peninsula is across the Red Sea from Africa. And so that's AFR on this diagram. And of course, Iceland, everybody knows that it's in between Greenland and Scotland. And so that's the other side of the Earth over here on the right-hand side, on the mid-ocean spreading center, right? And so it's the mid-ocean ridge. Here's the diagram that shows the Emperor seamounts and then also the Hawaiian volcanic chain here. And so the plate has moved over the top there. So we know the plates move. There's no doubt about that. In fact, the best evidence for plate movement is the fact that we can take GPS units now and we can actually measure how fast they're going. And so they're going like, 1 or 2 centimeters in some places. Well, that's the uplift rate. Maybe up to 10 millimeters in some places. And so there's a certain sort of a vector that these things have. So we can actually detect with seismic, you have one area and you watch how it's drifting and everything around it, right? So GPS is good for that. There is this idea, of course, that the Hawaiian Islands were over the top of a mantle plume. So in this next image here, there are 6 different slices of mantle tomography looking at what's inside the mantle directly underneath of the Hawaiian Islands. And they're showing you the orientation of the profile on there. So the first one goes from the south-southwest up to the north-northeast there. You can see that line that's on the little globe there. And that's what it would look like if you had a cross-section with the Hawaiian Islands directly in the middle of that slice, okay? There's not a discrete plume there, is there? It's like going off to the left and then it comes back to the right. If we look at the next slice here, that is more from the southwest to the northeast here. And there's no single discrete plume there either. And so you look at the next slice, and that's going from west southwest, right? You're going up to the east northeast, and you don't see a discrete plume. Here it's going to the right and then to the left, and you see the same thing up here in the next slice. That's the 4th slice here. And then at the very bottom row down here, you can actually see, there's a bit of a hot material there. But again, there's no discrete single plume like it's illustrated in any of these plume model illustrations for a mantle plume. So in other words, is the hotspot really related to upwelling of mantle there? So a hotspot is the tip of that plume. So the plume itself is the upwelling of material from the D double prime layer, we think. And that's that hot layer, a hot spot down here at the bottom of the images here. There's no discrete one. So some people think that these things could flicker, or it could be that maybe they just don't exist. Okay, so we don't have a good answer for it yet, I guess, is the summary of that. So we have this idea of plate tectonics, though. That holds. So plate tectonics, we know that there's subduction. We know that there's a seafloor spreading. We know that the plates move from GPS. How long have people known about that? Well, you have to go back a ways. If you go back into the 1500s, that's when people began to explore the entire Earth with sailing vessels, right? 1400s and the 1500s. And in the 1400s, they collected data so they would make charts and so forth of coastlines of these newly discovered continents, the New World we call it, right? North America and South America. If you compare the coastline of South America and Africa, they seem to fit together. So okay, let me try to do this. If this, okay, if this is Africa, South America seems to fit right in there like that, right? So in what are they? The Bonny Bight, they call that, right? So the Bight of Bonny in Africa is right here, and then Brazil fits right into that notch right there. They knew that in the 1500s. 1570s, there was a guy named Ortelius who made a map of the world, and he speculated it looks like South America was part of Africa at one time. Well, he was right, but he didn't know why he was right, So we know that he's correct today. It was Alfred Wegener. He was a German scientist in 1915. This is in World War I. Alfred Wegener published in German literature. He says, I think I've got good evidence for why I think these continents used to be together and then they broke up. And he was right too. They were together at one time and then they did break up, but his explanation for it was it's like an unbounded mass on the outside of a spinning top. And he thought it was centrifugal force that would cause the Earth's outer part. He called it continental drift. That's the earlier form of what we today know as plate tectonics. This continental drift, he said, well, if you put the continents back together like they fit, the mountain ranges sometimes go between the continents, and then we find plant fossils across some of these southern continents. So he recognized for the first time that there was a southern continent that was very, very long lived, but even it eventually broke apart. We call it Gondwana. So on Gondwana, there were some primitive reptiles, things that were like mammals almost, back in the Permian. So 250 million years ago, when all of these continents were back together, these animals roamed across that landscape. There were plants like Glossopteris who lived on these planets as well. And you can tie the continents back together with these plants. Well, they didn't drift across the ocean, in other words. They don't disperse that way. But in fact, they had to have walked across on dry land, right? And so for the longest time, people said, oh, plate tectonics, or they didn't say plate tectonics, they said continental drift. That's a crazy idea. There must have been land bridges that allowed these things to go from one continent to another. So in other words, they were more than willing to make some little narrow strip of land and say that the continents weren't together, okay? But Alfred Wegener, because this was 1915, he republished in 1919 after World War I. But it was in German literature, and so nobody read German in 1919 because the Germans lost the war. And he, in 1919, again in 1922, he said, I think this is the way it works. It's really kind of a sad case because Alfred Wegener was a great scientist, and he was actually a meteorologist. He studied glaciers of all things, and so he went to Greenland. The biography of Alfred Wegener is just absolutely astonishing. And he actually lost his life in Greenland. And so studying the flow of the Greenland ice sheet. But anyway, it was much, much later that people recognized as like, well, that seems to work, but what's driving this whole thing? And it took a guy named Harry Hess in 1963. I think he was at Princeton. And Harry Hess said, I think I got it. I think I know what does this. We know about seafloor spreading. So in between 1920s and then in 1963, people recognized that there were these mountains that were around the Earth in the deep oceans. And so they recognized there was a mid-ocean ridge that ran around. People then towed across magnetometers across the ocean floor, and they saw what they call stripes on the magnetic signature of the ocean floor. Because the Earth's magnetic field goes from north to south, and it switches every once in a while. So sometimes it's north up to the North Pole. Sometimes your compass needle would point to the South Pole because the polarity changes. And that the last time that happened was about 90,000 years ago. There was a little bit of a hiccup about 40-some thousand years ago as well. But it hasn't happened recently. But we know that the North Pole is shifting right now, so we're just not quite sure if it's going to flip again. So with Harry Hess, he said, we have these stripes on the seafloor that show symmetry around these mid-ocean ridges. There must be seafloor spreading there. And then on the opposite sides, people for the longest time knew about the ocean trenches that were around the Pacific, for instance, and they knew that there was some of the crustal material added to the continents there as well. And so if you've got this idea of subduction on one side and spreading on the other side, well, then it must work in tandem some way. And so the seafloor is spreading, new oceans will arise, the continents will break apart. And in fact, it took a Canadian to name this. The Canadian, he said, this is brilliant. This is a great idea. And he recognized that there were these supercontinents that may have formed, like Pangaea was all of the continents together at one time back 250 million years ago. Gondwana separated from that, and then later Gondwana broke up. So India was part of that. Australia was part of that. Antarctica, Africa, South America, and that's part of Gondwana. All of that was Gondwana. Asia, all of the plates that make up Asia, like the Siberian plate, there's the Eurasian plate. It's like that Eurasian plate is made out of a whole bunch of other plates, including South China and North China. And so North China and South China have collided as well. And so these continents have drifted across, but then they come back together. It was a guy from Canada. His name was J. Tuzlo Wilson. And so Wilson called this, there's this supercontinental cycle. Today we call it the Wilson cycle. But in fact, what you get is a series of supercontinents that will form and then break up. And he called it plate tectonics. And so Harry Hess put the idea together, and it was Wilson who then named it plate tectonics. And so that's how it works. So that's kind of where I'm going to leave it for right now. I've gone on long enough here, but we'll talk about plate tectonics in the next presentation. So anyway, thanks for your attention, and I'll be back shortly.